In this video, I am going to talk about the interface of solid vapor when we set a certain crystallographic plane as the free surface. And in this video, I am going to talk about the FCC crystal structure. This is the unit cell of FCC crystal structure, along with a plane with the indices of 1, 1, 1 shown on this unit cell. This right figure, you can see the arrangement of atoms in that closed pack plane, the plane of 1, 1, 1. We want to see what happens when we have this crystallographic plane as the free surface. Before everything, we should know how many atoms are in the vicinity of each atom in this crystal structure. The number of atoms that surround each atom in this crystal structure is equal to 12, because as you can see in this plane that the atoms are packed together, and here we have the mass density of all crystallographic planes in this crystal structure. There are 6 atoms around each atom. So first we have 6 atoms in this plane that are neighbor to each atom. We have other atoms in the lower plane and also in the upper plane, close to this plane that you see in this figure. So the plane that is under this crystallographic plane is shown by black atoms, as you can see here. The atoms are placed in these holes between these atoms in the other side of this plane, in the lower side that you can see as black holes, and the black atoms are placed in these holes. There are also other atoms in another plane which is placed above this red plane, and the atoms are placed in these holes that you can see here, and I show these atoms as gray atoms. So total we have 6 atoms neighbor to each atom in this plane, plus 3 atoms in the lower plane, because for example if we take this atom as our reference atom here that I mark it, we have 3 atoms, 3 black atoms in the other side, in the other plane that is under this plane and is equal to 3, and also we have other 3 atoms above this plane. So in total we have 12 atoms around each atom. When we choose this crystallographic plane as the free surface, it means that we won't have any other atom, for example in our direction, also in the direction outward of the screen. So it means that we remove these gray atoms and the other atoms onward. So we have this condition. It means that for each atom we remove 3 bonds. So we have 3 broken bonds when we set this plane as our free surface. If we want to calculate the surface energy of this plane when it is set as the free surface of the crystal, we should know the energy bond of each atom. So if we have the energy bond of each atom equal to epsilon, the share of each atom from this bond would be equal to epsilon divided by 2. So when we have 3 broken bonds, the amount of free energy that is posed on each atom is equal to epsilon multiplied by 2, epsilon divided by 2, multiplied by the number of broken bonds, which is equal to 3. So we have 3 multiplied by epsilon divided by 2. This epsilon is related to the latent heat of sublimation. Sublimation means that we have a phase transformation from solid to gas. It means that we break the atomic bonds in the solid state, and we have individual atoms in the gas state. If we want to relate the amount of epsilon to the latent heat of sublimation, we should bear in mind that the latent heat of sublimation that we show with Ls is equal to latent heat of melting plus latent heat of vaporization. And we can relate this amount to epsilon, because this latent heat of sublimation is expressed in the unit of joule per mole. Mole means the Avogadro number. So if we want to calculate epsilon multiplied by 2 for an individual atom, we should divide this latent heat of sublimation by Avogadro number, and if we want to have this transformation, we should break 12 bonds for each atom. So we have this amount divided by 12, and therefore we have the amount of gamma, the surface energy of the crystal when we have the plane 1, 1, 1 as the free surface, would be equal to 3 multiplied by Ls Na divided by 12. It is the combination of equation 1 and equation 2, which I write it once again, and we would have 0.25 Ls divided by Na. We can calculate this amount of free energy of the surface energy for other planes, which I explained it in our further videos. The unit of this quantity is, I write it here, joule per each atom on the surface.